In this video, I will be explaining two additional classifier algorithms called k-nearest neighbor and naive-based classifiers. So far, we have seen three different types of classifiers in machine learning. The first one was the logistic regression, which uses a sigmoid function, that is 1 plus e to the power of minus z, and the output of this sigmoid function is interpreted as a probability value which is used to classify the given observation. That was the in case of the linear discriminant analysis, we have seen that the linear discriminant analysis uses Bayes theorem to classify the given observation, and it calculates the probability, what it is called as the posterior probability. And in order to work the linear discriminant analysis, we need to have the sample data set in Gaussian distribution format or a normally distributed distribution. The third type of classifier system that we have discussed is the quadratic discriminant analysis. And in the quadratic discriminant analysis, the difference between the quadratic and the linear discriminant analysis is that in case of the quadratic discriminant analysis, we construct a class-wise covariance matrix, and that is used to uh, calculate the discriminating function value, which is used to assign the class labels. So this is the brief review of the three classifiers that we have seen so far. And in today's and in this video, I will be using two additional describing two additional classifiers. The first one is the naive based classifier, and the second one is the k nearest neighbor algorithm or KNN algorithm. So these are the two algorithms that I will be explaining in this video. And to explain this working of these two different classifiers, I will be using an example data set of employability that we have already seen, in which there are three input features are there called CGPA, communication skills marks, and the computer programming skill. And we are using these three different features to predict or to classify the students whether they are employable one or not, and one indicates the student is employable and zero indicates the student is not employable. So these are the this is the binary classification, and I am using this data set as the sample data set. Now, in case of the naive Bayes classification algorithms, uh, we need to represent the classification problem in terms of the concepts from probability. And to do that, uh, we are using the input. The input represents the n different vectors, like, or the n different features or independent variables, and these n different features and the independent variables are given as the input, and these inputs are already labeled, means that the Bayes classifier is a supervisory machine learning algorithm. And we need to calculate the output of the problem is that we need to calculate a probability value given that the observation or the n number of features, and we need to calculate the probability for the every class, that is the ck means every class labels. For a binary classification, there are two different classes are there, 0 and 1. In case of there are multiple multi-class classification problem, there are n number of class labels are there, and we need to calculate the probability of class label CK provided or given that n number of different features. So this is nothing but the this probability in the probability theory, it is called as the conditional probability. And one way to evaluate the conditional probability is by constructing a joint probability table that you might have studied in your course on probability and statistics, how the joint probability table is constructed. And using this joint probability table, we can evaluate the conditional probability. But the challenge lies here is that for a very large number of high dimensional feature vector, means when the number of features are very large and the data set is also very large, it is difficult to construct such joint probability table. And one way to evaluate this conditional probability, one of the effective way to evaluate this conditional probability, when number of features are very large and data set size of the data set is also large, then use the Bayes theorem. The Bayes theorem evaluates the is used to evaluate the conditional probability. And here there are the this is the equation or the theorem to evaluate the conditional probability. Here evaluating the probability of class label CK when the particular X observation is given is equal to, it is the ratio of two things. The first is the product of probability of CK, which means that a randomly selected observation belongs to class CK. And another, it is a product of another term that is called as, again it is a conditional probability, and this conditional probability is different from the probability that we are seeing on the left hand side of this equation. This probability evaluates that the randomly selected observation has value exactly X provided that the class label CK. To the probability of randomly selected observation has a value exactly X. So these are the three different probabilities are present on the right hand side of this equation. And these different four probabilities we are using, four probability term that we are using in these equations are labeled as, the first is the posterior probability. The posterior probability means that calculating the probability of each and every class label for given value of input vector, and this is also a conditional probability. The prior probability is the probability that a randomly selected observation belonging to the class CK, and this is the unconditional probability, or this is also called as the a priori probability. The third probability that is we are using here, that a randomly selected observation has exactly value X provided that the class label CK, and this is the conditional probability, and this probability is called as the likelihood. And the fourth probability that we are referring in this equation is the probability of X, which means that a randomly selected observation has exactly value X. And by using this terminology, the Bayes theorem can be put in the simple English terms like posterior probability is equal to the prior probability multiplied by likelihood of the probability divided by the evidence. So this is the Bayes theorem, and that is typically used when the input data set is very high dimensional, means that number of features are very large, and sometimes it is also used when the data set is small. So these are the two conditions at which you can use the apply the Bayes theorem to for the problem of classification. In these two slides, I have formulated the classification problem in terms of the probability. Now, the main thing when you decide to apply the Bayes theorem is to evaluate this equation. And in this equation, if you see, on the right hand side, there are three probabilistic terms are there. And out of these three probabilistic terms, the denominator term, that is P of x, does not refer to the class label Ck, and it is independent of the class label Ck. So that's why we can formulate this equation like this. The posterior probability, that is the probability on the left hand side of the equation, is proportional to the probability of on the equation that are written on the right hand side, which is nothing but the a priori probability and the likelihood. Means that the posterior probability is directly proportional to the prior probability and likelihood. Now, it is very easy to calculate the a priori probability given a data set, but we need to evaluate this conditional probability, that is the second term. And here we are assuming one assumption is that the given n input vectors or given n independent variables, they are independent to each other. If they are independent to each other, means there is no correlation between these n input feature. Then we can simplify this, we can calculate this conditional probability in terms of this equation. It is the product of conditional probability of individual vectors provided that the class level Ck. Means that in case of suppose that we want to calculate the a posterior probability of this particular third student ID, in this case this says that the conditional probability is the multiplication of, suppose that we want to calculate the probability for class 1, means 8.2, provided that the class level 1, calculate this probability, multiply this with probability of 6.8, provided the class level 1, multiply this with probability of 7.9, provided that 1, like this. So this is the probability for class C1. And similarly, you can calculate the probability for C class level 0, probability of C0, like P 8.2 provided 0, P 6.8 0 and P probability of 7.9 provided 0. So this is the way in which you can evaluate this likelihood. And the product of this, when you multiply with the a priori probability, you will get two different uh, probabilities value in case of the binary classification. In case of the multiple classification, you will get as many values, probability values, as there are the number of class labels. So in case of the binary classification, you will get two values. Like here, suppose that C1 refers to the first value, C0 refers to the second value. Now, in order to assign the class label, you need to select the highest one out of these. This expression tells that select the maximum or the highest one, and that is your class label. So this is the rule or logic that is used to when you apply the Bayes theorem to assign class labels. Now, when you are deciding the class labels, when you have decided to use the Bayes theorem to calculate the condition likelihood, then the one of the challenge is to find the evaluate the likelihood probability, and this likelihood can be calculation of this likelihood can be made simplified if you assume certain things. If you assume that your data set is has the normal distribution or Gaussian distribution, then the likelihood is calculated by using this equation. In this equation, pi is the prior probability, sigma is the standard deviation, and mu k is the mean, class-wise mean. So using these population parameters or the sample parameters, you can evaluate the likelihood by using this function. So if you are assuming that your sample or the population has the Gaussian distribution, then that kind of uh, when you apply with this assumption, those classifiers are called as the Gaussian naive Bayes algorithm. And in this see here, in this Gaussian naive Bayes classifier, we are assuming that our population or the sample has the normal or the Gaussian distribution. Normal or the Gaussian distribution means that when you plot the frequency values, you will get the bell-shaped curve for input vector or the independent variable. And on the here on the y-axis there are the frequency of the individual values. So if you plot this graph, then you will get the bell-shaped curve. So if your population or the sample, if you are making this assumption, that kind of Bayes classification is called as the classifiers are called as the Gaussian naive Bayes classifiers, in which likelihood function is calculated using this function. Now, second type of naive Bayes classification is called as the multinomial naive Bayes classification, and it is typically used for the text classification. And in this case, each input vector or independent variable represents the count of a particular number of times a particular event has occurred. Or if you are using it for the text classification, the value of the independent variable represents the number of times a particular word occurs in a particular document. And a multinomial means that if there are n number of input vectors are there, then for n number of input vectors, there are n probability values are there. And those probability value represents the probability of occurring that particular term. And if you are assuming this kind of data set, then the likelihood function that you will use is this one. Here this sigma symbol represents the sum of xi for all I and take this factorial. Then pi is the product. Here this pi is the product, and this pki is this class specific probabilities of the individual terms. And this kind of distribution is called as a multinomial distribution, and it is particularly used for the text classification. Now the third type of naive Bayes classifier is the Bernoulli naive Bayes classifier. In this case, we are assuming that the independent variables are the Boolean variables or the binary variables, means that the values of the independent variables are text 0 and 1. If you are assuming making this assumption, then this is the likelihood functions that you are going to use. And this is also used for the text classification. And 0 represents that the occurrence of a particular word in a document, or sorry, 0 means non-occurrence of a particular word in a document, and 1 represents the occurrence of a particular word in that document. So the Bernoulli naive Bayes documentation input features are Boolean variables. You can use different modules. Many machine learning libraries are available to evaluate the likelihood function. In case of you are using the Python language, then the scikit library provides these many modules uh, called Gaussian naive Bayes then multinomial Naive, then Bernoulli Naive to evaluate the likelihood function. Now the another type of classifier algorithm that I would like to explain in this video is called as the k nearest neighbor classification algorithm. Like in the previous algorithm, this is again the supervised machine learning algorithm, means that you need to provide a data set, a labeled data set, and it is very easy to implement in its the most basic form, but it can be applicable to perform the quite complex classification task like image classification, object recognition. For that kind of task also you can use the k nearest neighbor algorithm. It is a lazy learning algorithm, means that you does not require to train and test phases are there. During the test phase, it goes on learning the rules of the classification. KNN is a non-parametric learning algorithm, means that it does not make any kind of assumptions. Like in case of the logistic regression, we assume the shape of the function is like this. In case of LDA and the QDA, we assume that our sample data set has the normal distribution like this. But the k nearest algorithm does not assume any shape of the underlying shape for the function. And that's why it is called as the non-parametric algorithm. And this relaxation is and many real life situation does not fit into such kinds of models like the Gaussian distribution or assumption that we make in while logistic regression. In those cases, you can apply the k nearest algorithm, and this algorithm is very simple one. Here k is here the k is an any integer number, and this integer number is given, or you need to select a integer number, and this is on the left hand side of the figure is a scatter plot for a in which shows the classification of in two different categories. Like one category is the blue dots, another category represents the red dots, and this is the two-dimensional classification problem x1 and x2, and this is the scatter plot. Now suppose that you have new test data is available, and you can use and have suppose that the new test data is represented here by x. Now here we need to identify whether it should be colored with red or whether it should belong to the blue category. And suppose that the value of k is 3. Now what this algorithm does is that it identifies three data observations which are nearest or the closer to this test data set x, and these are the three nearest observations. So this is the first, this is the second, and this is the third. And if you see that out of these three observations, the two observations belongs to the red class, and that's why the red class is assigned to the test data. So this is the working of the uh, k nearest algorithm. And in this k nearest algorithm, you need two things. One is the you need to decide the value of k, and you need a function to identify the nearest data observations. And for that, you can use the distance formula like Euclidean distance. Euclidean distance formula is that x1 minus x2 whole square plus y1 minus y2 whole square and under root. So this is the Euclidean distance formula. So you can use this distance formula to identify the k nearest observations, and out of those k nearest observations you can select which is the having the largest number of observation that belongs to a particular category. That category or that label is assigned to the test data. So that is the working of the k nearest learning algorithm. Here I have given the algorithm for the k nearest classification. Now the k nearest algorithm has some advantages and disadvantages. The advantages are like this: it is extremely easy to implement. It is a lazy learning algorithm and therefore requires no training prior to making the real-time prediction. So there are no training phase and the test phase. Since the algorithm requires no training before the making predictions, new data can be added seamlessly as you need to test. There are only two parameters that you need to fix. One is the value k and another is the distance function. One example of the distance function is the Euclidean distance. The k nearest algorithm, the disadvantages of k nearest algorithm reads like this. The k nearest algorithm does not work well when the high dimensional data set is available. Because the large number of dimensions, it becomes difficult for the algorithm to calculate the distance. The KNN algorithm has a high prediction cost for a large data set, and the KNN algorithm does not work on the categorical data. So if you have categorical data, then it is not possible to use the KNN algorithm. So this is about all the k nearest algorithm and naive Bayes algorithm. Thank you.